Hi Year 12, today what we're looking at is geometric growth and decay. So we can use geometric sequences and series to describe growth and decay in practical problems. This is called geometrical growth and decay. It is also called exponential growth and decay because Tn is equal to a r to the power of n minus 1, and this is an exponential function because we have our power or our unknown in our power. So we have our first example here, and we have a layer of tinting for a car window light lets in 95% of light. We want to know what percentage of light is let in by 2 layers of tinting. So what we have to do here is we need to change our percentage to a decimal. So our 95% is 0.95. So 2 layers of tinting, what we have is we multiply the layer by itself. So we'll have 0.95 times 0.95 or 0.95 squared is equal to 0.9025. Now we just want to multiply this by 100 to get it back as a percentage. And to get it back as a percentage, it's 90.25%. So therefore, this means that 2 layers of tinting is 90.25%. Now, to work out 10 layers of tinting, it's a little bit trickier. So we have our 0.95 and our 0.9025, because we know that 1 layer of tinting lets in 95% of light, or 0.95. 2 layers of tinting is 0.9025. So we could just keep multiplying by 0.95 to work out what percent 10 layers of tinting lets into the car. But that's going to take us a little while. So what we want to do is we want to use our, we're trying to find the 10th term here. So we want to use our term formula for geometric sequences. So we'll have Tn equals a r to the power of n minus 1. And this is where we have our a is equal to 0.95. We have our n is equal to 10. And our ratio is equal to that 0.95. Okay, because what we're doing is we're multiplying by that 0.95 each time that we add a layer of tint. This then gets us that T10 equals 0.95 times 0.95 to the power of 10 minus 1. Okay, this is then just 0.95 times 0.95 to the power of 9, which I suppose is the same as 0.95 to the power of 10, okay, using our index laws. So when we put that into our calculator, we get 0.598736 ... Again, we want this as a percentage because we've been asked what percentage of light is let in. So to get it from a decimal back to a percentage, we want to times by 100 to get out 59.87%, and that is rounded to 2 decimal places. Now, the question doesn't ask us to specifically round to 2 decimal places, so we just want to write it off to the side in the corner. Our part B of this question asks us how many layers will let in 40% of light. So what this means is we need to we want to find when is Tn equal to 0.4, okay, for what nth layer, and that's 0.4 has come from 40%, just converting it back to a decimal. So again, we want to use our Tn formula, a r to the power of n minus 1. This is where we have our a is equal to our 0.95 again. We have our r is still equal to 0.95, and we have our Tn is equal to 0.4. In this question, we are trying to find n, so n is our question mark. We'll have 0.4 is equal to 0.95 times our 0.95 to the power of n minus 1. Okay, what we can do here is we can use our we can use our index laws of a to the power of m times a to the power of n is our a to the power of m plus n to get 0.4 is equal to 0.95 to the power of n. Now we're solving for n, so I'm hoping you're sitting there saying you need to use log BAP, which if you are thinking that, you are correct. So we want to use our log BAP, so base power equals answer is what we currently have, and we want to convert it to log of base A equals our power. This means we're going to have log of 0.95 of our 0.4 is equal to our n. So we can put this straight into our calculator. So n equals 17.86 375,281. Okay, and so we want to know how many layers of light will let in, 40% of light. We can't have point layers, so we are going to round up so that it is 18 layers for n. So therefore 18 layers will let in 40% of light. Okay, moving on to question 2. Question 2, we have a certain kind of washing process remove 60% of stain on a fabric. What proportion of the original stain is removed by 3 successive washes? So what we have is that it removes 60% of the stain. So what this means is there is 40% of the stain remaining. So that means that T1 is equal to 40%. I suppose we should probably write that down. Okay, but we want to be working in decimals, so it's equal to 0.4. That means that T2 is equal to 0.4 times 0.4. Okay, because at every time we wash, it removes 60%, leaving 40% left. That means T2 is equal to 0.16. T3 is equal to 0.16 times 0.4, so timesing by 0.4 each time, and when we get that, we get 0.064. Okay, times it by 100. Sorry, I haven't really left you enough lines here, have I? It equals 6.4%. Okay, so what that means is our little what this means is there is 6.4% of the stain remaining. I really didn't leave you enough lines, sorry. Remaining. So we need to work out how much was removed. So we want to therefore have 100 minus our 6.4% equals our 93.6%. So therefore 93.6% was removed after 3 washes. Now it's really important that we are changing this to be how much stain is left. If you were to do it the other way, you would not get the same result for this. Okay, so it's really important that we are doing it in this direction. So now we want to work out how many washes are needed to remove 95% of the original stain. So what we need to work out is how much stain is left, and that is our Tn that we're dealing with, and it is our 0.05, and that is how much stain is left. Okay, we are using our same starting value. So our starting value is our A, we want to be back in pink, is our A equals our 0.4 because we're removing 40% each time, and our ratio is 0.4 as well. and we have our n equals our question mark. That's what we're trying to find, is how the number of washes. So we want to use our Tn formula, which is AR to the power of n minus 1, where Tn is our 0.05, which was our 5%. Our A is our 0.4 times our R of 0.4 to the power of n minus 1. Now, again, we want to use that index law, A to the power of m times A to the power of n equals A to the power of m plus n, to get our 0.05 is equal to 0.4, okay, because we have 1 plus n minus 1 is just 0.4 to the power of n. Again, we want to use our log BAP formula, so we are converting between our base power equals our answer, and so what we'll have is we'll have log of 0.4 of 0.05 is equal to n, and so n equals 3.27 ... in our calculator, so therefore it must take 4 washes to remove at least 95%, to remove 95% of the stain, okay? Because if we only did 3 washes, we wouldn't have got 95% of the original stain gone. Cool. All right, question 3 is more like our financial maths, which you guys have all been waiting for. So we have a car bought for $35,000, depreciates our lost value by 12% per annum. We're going to find its value after 1 year. So when something's depreciated, we can use our compound interest formula, which is our A equals P lots of 1 plus R to the power of n, is our compound interest formula, and we have that on our reference sheet, but we are going to want to be using our A equals P lots of 1 minus R to the power of n. Okay, that is our depreciation formula. So what we have here is, when we're using this formula, we have our P is equal to our amount of money. So our amount of money is our $35,000, so write that down. Our R is our rate, which is 12% per annum, which is 0.12. And in this case, our N is equal to 1. We substitute all 3 of these values into our formula. So A equals 35,000, 1 minus our 0.12 to the power of 1. Put that into our calculator and we get A equals 30,800. Okay. From here, question 2, or find its value after 2 years. Same scenario. A equals P lots of 1 minus R to the power of n. Our P is still our 35,000. We have that our R is our 12%, which is our 0.12, but our N is equal to 2 this time. So what we'll have is A equals 35,000, 1 minus 0.12 to the power of 2. So we'll get A equals 27,104. Okay, for number 3 years, we'll have our formula A equals P lots of 1 minus R to the power of n. Same dealio, P is 35,000. Our R is 12%, which equals 0.12, and our N is equal to 3. We'll have A equals 35,000 lots of our 1 minus our 0.12, all to the power of 3. Put that into your calculator to get $23,851.52 at the end of our third year. That's what our value will be. Now, what we want to do is we want to write the value of the car as a sequence. So what we have is we have our 30,800, we have our 27,104, we have our $23,851.52. That is our sequence of our values. Now, what we want to do for part C is we want to find what the car is worth after 10 years. So we want to find the TN formula here. So TN is equal to AR to the power of N minus 1 is what's going to be helpful. Our A is our first term in our sequence. So our first term in our sequence is our A equals our 30,800. Our N is equal to 10. And our R is equal to our 27,104 divided by 30,800, which equals 0.88. Okay, which makes sense because 1 minus 0.12 is 0.88. So that's what we've been multiplying by each time. So our T10 is equal to our 30,800 times our 0.88 to the power of 10, okay, or 10 minus 1, sorry, n minus 1, whoopsies. All right, so this is then equal to our 30,800 times 0.88 to the power of 9. We put this into our calculator and we get 9747.53416, which is equal to $9,747.53. That's what the value of the car is worth after 10 years. Now, the whole point of this exercise is we're using geometric sequences and series. Yes, you can use the compound interest or the depreciation formula for this. If we were to use the formula, it would be A equals P lots of 1 minus R to the power of N. It'd be A equals our 35,000 still, because that was the initial value of the car, 1 minus 0.12 to the power of 10, okay, which then gets us our 9747.53416. A equals our $9,747.53. Now, I can hear one of you saying, hey, miss, but why have we not got 35,000 as our first value of the car as a sequence? And that is because we have N equals 1 is our first value of the sequence. So this here is our N equals 1. This is our N equals 2, and this is our N equals 3. Our 35,000 is our N equals 0. It's our initial value. So we don't use it in our geometric sequence or series for this. Sequence, the series is when it's plus. Okay, so part D of this question is when will the car drop below $15,000? And we want to answer to the nearest year. So what we are going to do is we want when will it equal $15,000. So we're using our TN formula equals our AR to the power of N minus 1. And we are going to go, what we're going to do is we're going to let TN be less than our 15,000. Excuse me. So we have our A is same as the last question, 30,800. Our R is 0.88, and our N is what we're trying to find. We have our TN, we don't know. So what we have is we'll have our instead of our TN, we're going to have our AR to the power of N minus 1. So we're going to have our 30,800 times our 0.88 to the power of N minus 1 is less than 15,000. Now, what we're going to have from here is we're going to need to get rid of that 30,800. So we're dividing it to both sides. leaving us with 0.88 to the power of n minus 1 is less than 75 on 154. Now, we're going to need to log back this, but we have an inequality. So we are going to, from here, we are going to say let 0.88 n minus 1 equal our 75 on 154, and we need to use our log BAP with this. So log base answer equals power, base power equals answer. To convert it from exponential form to log form, we'll have log of 0.88 of our 75 on 154 is equal to n minus 1. We're going to plus our 1 over now so that we get n equals log base 0.88 of our 75 over 154 plus 1. And we're going to put this all into the calculator at the one time. When we put this into our calculator, we get 6.628142852. So n, right, we need to know when will the car drop below 15,000. So we're going to let n equal 7 here. All right, we're just going to do a little check off to the side. So check, we have t of 7 is equal to 30,800 times 0.88 to the power of 7 minus 1. Put that into your calculator, 30,800 times 0.88 to the power of 7 minus 1 is equal to 14,303.65 cents. Okay, so that means that, therefore, it will take 7 years for the car to be less than 15,000. Some dollars. Cool. All right. We can also use our limiting sum model to model some types of problems. So we can write repeating decimals as fractions using our repeating sum. So what we have here is our 0.5 repeater. Now that is equal to 0.5555 ... Okay, and using our knowledge about units all the way back from primary school in year 7, what we have here is we have 5/10 plus 5/100 plus 5/1000. ... Okay, so what this means is using our limiting sum formula of S equals A over 1 minus R, where we have our A equals 5/10, our R is equal to 1/10. What we have is that our S will equal 5/10 divided by 1 minus 1/10. So that is 5/10. 1 minus 1/10 is that is equal to 9/10, but we want to KFC this at the same time because we're smart enough to do it all at once. So it will be times 10/9, which equals 5/9. So we can convert our repeated decimal to 5/9. If you were to put 5/9 into your calculator, convert it to a decimal, you'd get that it's our repeat of 0.5 repeater. Okay. Our last example, really quickly, is that a ball is dropped from a height of 1 meter and bounces up a third of its height. It continues bouncing, rising a third of its height on each bounce. We want to draw a diagram showing the motion. So the ball starts at a height of 1 meter and it drops down to the ground. It travels 1 meter. It then goes up a third of its height. So it goes up to 1/3 of a meter. It then has to bounce down 1/3 of a meter. It will then do 1/9 of a meter and then bounce back down 1/9 of a meter. It will then bounce up a 1/27 of a meter and bounce down a 1/27 of a meter. So multiplying by 1/3 each time. Eventually, what's going to happen to the ball? It's going to stop eventually, okay? What we want to do in our part B is we want to work out our total distance. So our total distance is going to be that it travels 1 meter plus 1/3 plus 1/3 plus 1/9 plus 1/9 plus 1/27 plus 1/27 plus ... Okay, what you'll notice here is we have 1 plus we have 2 lots of 1/3 plus we have 2 lots of 1/9 plus we have 2 lots of 1/27. So what plus ... So what this means is we have 1 plus 2 lots of 1/3 plus 1/9 plus 1/27 plus ... So we can factorize out that 2. This is where we have 1/3 plus 1/9 plus 1/27 is a geometric series. We can then use our limiting sum formula. So our limiting sum formula will help us calculate our sum. It's a limiting sum because it's going to stop. So limiting sum is S equals A over 1 minus R. This is where our A is 1/3. Our R is also 1/3 here. Okay, what we'll have is S equals 1/3 divided by 1 minus 1/3. Okay, we can put that into our, we'll get 1/3 times by 3/2. So we get 1/2. We could have just put it into our calculator as well. That's completely fine. Okay, this means that therefore we are going to replace our sum here. Our geometric series is going to be replaced by 1/2. So that means that our, we're still in highlighter mode, sorry. This means that our total distance is going to equal 1 plus 2 lots of 1/2, which is equal to 1 plus 1, which equals 2 meters. So therefore, the total distance the ball travels is 2 meters. Cool.